Hello, I'm Tuyen Tran from Deakin University, and I'd like to introduce our work titled Planner Refiner, Dynamic Space-Time Refinement for Vision-Language Alignment in Videos. This research addresses one of the key challenges in video understanding. This challenge is how to connect complex natural language descriptions with the dynamics of visual scenes. The challenge comes from the fact that current vision language models perform well when the description is short and simple, but they struggle with long compositional queries that describe a sequence of actions. For example, find the horse that turns left, swings its tail, and strikes another horse. These complex sentences require the system not only to recognize objects, but also to reason about how they move and interact over time. In this presentation, I will go through each section, including motivation, method, and the experimental results. First, start with the motivation behind our work. Looking at the right part of the poster, I showcase the difference between ours and previous work. Currently, most existing models reduce a complex sentence into a single embedding and try to align the entire embedding with video features. This approach failed to capture the compositional structure. The structure here, what I mean is relationships between nouns, verbs, and their temporal order. Then the model cannot truly understand multi-step actions. Another limitation is that most benchmarks contain only short, simple descriptions, which means models are never evaluated in realistic multi-action scenarios. Our goal is to bridge both gaps, to design a framework that performs compositional reasoning, and to provide a benchmark that tests this capability properly. Now we move to the method section. At the core of our solution is the Planner Refiner framework, which consists of two key modules working together. The first is the language-based step planner, which takes a complex sentence and decomposes it into a sequence of smaller subprompts. Each subprompt contains a noun phrase and a verb phrase, essentially describing one atomic action in the sentence. For example, the query, panda lying down and eating, is decomposed into panda lying down and panda eating. We use rule-based algorithm with constituency parser to identify this structure, so the number of subprompts adapts to the linguistic complexity of the sentence. In this way, the planner produces an ordered reasoning plan for the model to follow step by step. Once we have this plan, the language-guided visual token refiner takes over. I will first explain the intuition before going into the detailed implementation. Intuitively, our system operates as a recurrent process that iteratively refines the video representation according to each subprompt. At every step, the refinement occurs in two stages. First, a spatial refinement guided by the noun phrase to localize the relevant object, and then a temporal refinement guided by the verb phrase to capture how that object moves or changes over time. These spatial and temporal attentions follow the same order as natural language, nouns first, verbs second, allowing the system to progressively align vision and language in an interpretable way. Each iteration further improves the representation, producing a fine-grained alignment between what is described and what actually happens in the video. This recurrent design is not only more interpretable, but also more efficient than joint space-time attention, reducing computational complexity while improving reasoning quality. Now, for the concrete implementation, we start with two inputs, the video and the language description. The video is first passed through a visual encoder, which produces a set of visual tokens. Each token represents a spatio-temporal region in the video, so the overall feature has two dimensions, one along space, corresponding to features within each frame, and one along time, corresponding to features across different frames. Meanwhile, the language has already been decomposed by the planner into several noun-verb pairs, where each pair describes one atomic action in the sentence. Now, for each of these pairs, the refiner updates the video tokens through two self-attention operations. In the first stage, we handle the noun phrase. We take the noun embedding, for example, panda, and concatenate it with all visual tokens. This combined representation goes through a spatial self-attention block, which refines the spatial relationship between visual tokens under the guidance of the noun. Then, in the second stage, we do the same but with the verb phrase. We concatenate the verb embedding, such as eating, with the refined visual tokens from the previous step, and feed them into a temporal self-attention block. This attention runs along the time dimension, allowing the model to reason about how the object changes or moves across frames. This process repeats recurrently over all subprompts, so the representation becomes more precise with every step. Finally, the refined visual tokens are passed into task-specific heads. Segmentation head for referring video object. Segmentation or a temporal prediction head for video grounding, as did in other works. Finally, let's look at the results. Here we showcase the performance of our method on the proposed MeViS-X benchmark. In this figure, we compare Planner Refiner with the state-of-the-art method DSHMP across different sentence lengths. What's interesting is that while both methods perform similarly on short, simple queries, our model shows increasing advantages as the sentence becomes longer and more complex. In other words, the more compositional the input description, the greater the performance gap. The red line here indicates the relative improvement of our approach over DSHMP, which steadily rises with sentence length, highlighting how Planner Refiner handles complex multi-action queries more effectively. Thank you for listening. You can find the paper and code from these links. If you have any questions, feel free to contact me. I am more than happy for any discussion.